Hello, Math 2. This is Mrs. Bricky, and this video is for Unit 11, Lesson 3. We're going to be talking about frequency tables and determining dependency. Okay, so we've been working with two-way tables. So this is a two-way table that tells us about a population of 48 guppy fish that are in an aquarium. So some of the fish are orange, some of the fish are blue, some of the fish are male, and some of the fish are female. So we've got all of our data right there. We are going to turn this into a frequency table. So this two-way table that we're starting with up here, this is a table that's showing us quantities. A frequency table tells us or shows us frequencies, or really you can think of them as probabilities straight away. So the way that you get each frequency is you take the value in each cell and you divide it by the total. So if I do 5 divided by 48 and I round my answer, I get 0.1. So a couple of these values are filled in. We're going to fill in the rest of them. So for this second cell, we're going to take the 13 and divide it by 48. And that gives us 0.27. And we're going to take the 12 in the next row right here and divide it by 48. And that gives us 0.25. And we just continue filling that in with these quantities. So the next one, 18 divided by 48. And then this one right here is going to be 30 divided by 48, which gives us 0.63. And the bottom row, 17 divided by 48 gives us 0.35. And then our last cell, 31 divided by 48, 0.65. Oh, sorry, that was a 3.8. I don't know why I wrote 3.5. Okay, so these quantities, you might notice that this table in particular, and I sort of chose this one on purpose, but you notice that these two numbers do add up to 0.35, and these two numbers do add up to 0.65, but we kind of have a little problem in the rows. They don't look like they're adding up quite right, so this can sometimes happen in a table. I chose to round to 2 decimal places, and so when I rounded, the 0.1 and the 0.27 don't exactly add up to 0.38. They add up to 0.37. This number really is 0.375, and it's being rounded up to 0.38. So you may have or may notice or see tables occasionally where the totals don't seem to add up quite right, and it is usually just because of how the quantities were rounded. Like if I had chosen 3 decimal places instead of 2 decimal places, we probably wouldn't see that same thing happening. Anyway, so the point is maybe just don't look and pay attention to things like are the columns adding up, but it could be not adding up perfectly because of an issue with rounding. Okay, so now that we have this frequency table, one of the things that make frequency tables kind of great is it makes it easier to answer probability questions in some cases, because the relative frequencies are the probabilities of each outcome. So if I'm interested in the probability that a fish picked at random is orange, then I can just look at this number right here. That tells me that the probability that a randomly picked fish is orange is 35% or 0.35. The next question says, what is the probability that a fish picked is an orange female? So they need to be orange and they need to be female. Both female and orange. Here are my orange female fish, 0.25. Okay, so the next questions are going to switch over to some conditional statements. So this one says, what is the probability that a female fish is orange? So this is my given. I know that the fish is female. I'm wondering what's the probability that that female fish is orange. So this is, oops, sorry, meant to write a P for probability. This is the probability of getting an orange fish given that we know it is a female fish. So we've done this with quantities before, and it works exactly the same way with frequencies. So the given condition tells me that I'm limited to thinking about this column. I know that the fish is female. I'm wondering about the probability that the female fish is orange. So it's going to be out of all of the females, and it works with frequencies. Wow, I can't write the numbers that I mean to write today. 0.63 is the total female fish frequency, and then the orange ones from that group, 0.25. So in this case, we will divide that in our calculator, and we get if we round 0.040, 0.40. So 40% of the female fish are orange. All right, let's do the next one. What is the probability that a male fish picked at random is blue? And again, being male is a given condition. We know we have selected a male fish. We want to know what's the chance that he is blue. So this will be out of, we're looking at that top row now. It's going to be out of 0.38, and the male ones that are blue, 0.27. So if we divide that, we get our probability, which is 0.71, 71%. Okay, last one with this table. We want to know what is the probability that a blue fish picked at random is male. So I reach into the tank, I grab a blue fish. This is my given condition. I know I'm grabbing a blue one. And I want to know what's the probability that the one I pick is male. So it's going to be out of, we're focusing on blue fish here, so it's out of 0.65. And the male ones are 0.27. So if we divide that, it gives us, if I round, 42% or 0.42. So to get any of these probabilities, it wouldn't be necessary to have a frequency table. We could have gotten all of these probabilities from this table. But sometimes this is the type of table you're given from the get-go. Sometimes you are just given a frequency table, and so you can get the probabilities from the frequency table really in just the same manner that you do from a two-way table that has quantities. All right, here is another example. A pharmaceutical company is testing a new medicine for a disease. They've got 115 test subjects, and some of the test subjects are given medicine, others are given a placebo, and we've got this data in a frequency table. So if one of these test subjects is selected at random, let's find these three probabilities. So the first one is the probability that symptoms persist. So again, we can just grab that right from the table. The nice thing about frequency tables is that they are often pretty fast. Probability that they're given medicine and they have symptoms that persist. So just both of these characteristics, given medicine and symptoms persist, that would be a 0.23 probability, or 23%. The next one, given a placebo or their symptoms persist. So this one's a little tricky because we need to think about all of the ones who are given a placebo. So that would be, all of this group, so 0.5. But there's a few more. We also just are wondering, maybe their symptoms persist, so we also want to add these 0.23. Basically, this is the same as the probability that they are, that they are it's like everybody else except the people that are given medicine and have no symptoms. So it'd be 1 minus the probability that they're given medicine and have no symptoms. And if that's a tricky thing to think about, you don't need to think about it that way, but when you see an or like this, you do just need to think about all of the people that includes. So it would be these three groups. These are all of the people who are either given the placebo or their symptoms persisted. And so we just add that together to get 0.73. Okay. And I have just a couple more questions underneath here. Based on the information in the table, do you think that being given medicine has an impact on whether or not the symptoms persist? Like, what could we think of to help us decide if we think that the medicine is helpful? Well, something we could think about is we could think about what's the probability that they have symptoms still, given that they had medicine, and compare it to the probability that they have symptoms given that they got the placebo. Like, is the medicine making a difference or not? So for this one, we would divide it out of the total who were given medicine. So this would be out of 0.5, half of them were given medicine. And those that had symptoms were 0.27. So dividing, oh, sorry, that's no symptoms. Silly me, sorry. No symptoms. We want symptoms. Symptoms persist, 0.23. And so if we divide that, we get 0.46. Now to think about those that are given the placebo and have symptoms persist. So this will still be out of 0.5 because half got the placebo and half got the medicine. So we're out of that 0.5. And of that group, the ones that had symptoms persist, 0.36. So if we divide that, we get 0.72. So if you were given the medicine, you had a 46% chance of having symptoms. But if you were given the placebo, you had a 72% chance of having symptoms. So to me, that kind of helps me to understand or to see that maybe the medicine did have an effect, because they were a lot less likely to have symptoms when they were given the medicine. So there's other ways you could think about answering this question. It's pretty open-ended here, but that's one of the things you could think about. Okay, for this example, we have a little, it's called a tree diagram. So the tree diagram is sort of dividing out a group of people. So 1,000 people were given a skin test for tuberculosis, and they're testing this new skin test. So they know some of these patients have tuberculosis and they know some of these patients do not. And then they looked at how the test came back. So they're testing the tuberculosis test. So this is telling us, this first branch of the tree right here is telling us that 380 of the patients have TB, 620 of them do not. And then of that group of 380, 361 tested positive and 19 tested negative. And then for the other group of the patients that don't have TB, 62 tested positive and 558 tested negative. So we're going to create a frequency table from this information, and then we'll use it to answer some questions. So first of all, our first classification is either the patient has TB or does not have TB. So let's put those two here. And we're going to create a frequency diagram. So we want decimal values here. So we need to think about maybe the probability that the patient has TB, or the frequency that they have TB, and the frequency that they don't have TB. And these are totals. So it was out of 1,000 patients. So for the patients who have TB, that's 380 out of 1,000. And so that's 0.38. And I'm going to keep 3 decimal places for this example. And then for the patients that do not have TB, that would be 0.62. And again, that just comes from taking that number divided by 1,000. Okay, so that's our totals for whether the patient has or does not have TB. And so now from that group that has TB, some of them tested positive and some of them tested negative. So the ones that have TB and tested positive, there's 361 of them. So my two categories here need to be that they test positive or they test negative. They're in one of those groups. So this would be 361 divided by 1,000. And then it would be 19 divided by 1,000 for those who tested negative. So I took this 19 and divided by 1,000. So I know this, like these 19 people, they have TB and they tested negative. Okay, so for the next column, we're going to use these two branches down here. We have 62 people who tested positive and do not have tuberculosis. So that would be right here, 0.062. And for those who don't have TB and tested negative, that would be 0.558. It's kind of nice when we're dividing by 1,000. Okay, and then we can just total these rows up by just adding them together. 0.423, 0.019 plus 0.558 is 0.577. And then the rows and the columns should add up to 1, barring that small, sometimes rounding difference. Okay, so we've got our frequency table filled in. So let's answer a couple of questions. You may have noticed that 380 patients have TB, but yet not all of them tested positive. Medical tests are not perfect. In stats notation, tested negative given TB means like the number of patients who tested negative given that they have TB. I want you to determine the probability that a person who has TB received a negative result. So the given condition is we know that they have TB, and we want to go figure out the probability that they get a negative test. So it's out of the group that has tuberculosis, so it's out of 0.380. So I'm using this column right here, and then we're looking for the ones that tested negative, so 0.019. So if we divide those two numbers, we come up with 0.05. So that means that if you have TB and you use this particular skin test, there's a 5% chance that you are going to test negative, even though you have the disease. So next question. What would you say to a friend regarding the validity of their results if they're testing for TB using this skin test and the results came back positive? So if you got this skin test and you got a positive result, or your friend, it's not a guarantee that you have tuberculosis. So let's do a probability to help us, maybe tell our friend what the likelihood is that they actually have TB. So the thing that we know is it is known that the result came back positive. Whoops, sorry, that's not where the known goes. It is known that they test positive. So that's our given condition, and we want to know, what is the probability that they have TB, knowing that they got that positive test result back. Whoops. Okay, so the group that we're thinking of, or the subgroup that we're thinking about, are the people who test positive. So it's going to be out of 0.423, and of that 0.423 of that group, the ones that have TB are 0.361. So if we divide that, that's a 0.85. So if you get a positive result, there's an 85% likelihood that you have the disease. And tuberculosis is not unique in this. If you get a positive test result, what that tells your doctor is that they need to do follow-up. It means that they need to maybe test again, or maybe they need to do a biopsy, or maybe they need to do a more accurate test. It's just a way of trying to identify people who have the disease, but it's not. Most medical tests are not perfect. So, Part C, in this situation, explain the consequence of errors if you have a test with incorrect results. So, if you test negative but you have TB, the consequences, like, you might not be getting the treatment that you need. So you might be having symptoms that are bothering you, but your doctor's like, no, you don't have it. You tested negative. So it's problematic. The consequence of having a negative test when you have a disease is that you're not getting treatment. But if you don't have the disease and you test positive, that's also somewhat problematic. It might mean that you're getting extra treatments that you don't need. It might mean that your family thinks they're at risk of this disease genetically, but they're not because you didn't actually have it. There's also consequences if you test positive and don't have the disease. So given if a health test is not 100% certain, why might it be beneficial to have the results lean more towards a false positive? So false positive means that you get a positive test, but you don't have the disease. So I think generally when we're talking about diseases, we want to be able to treat diseases so that people have better lives. So we would rather, so it's a little bit more beneficial to accidentally think someone has it than it is to not catch it. If you don't catch a disease, it could end up killing somebody. So definitely a lot of tests err towards that false positive. Okay. All right, next part. That last part of the video should give you all the information you need to do the front side of the assignment. All right, the back part, we're going to be talking about Part B, checking for independence using probability. So sometimes you can just consider a situation when you're deciding whether two events are independent. Like we had some worksheets earlier in the unit where you had to read about a situation and decide if it was independent. But however, like a lot of times you can't just think about the situation and decide if it's dependent or not. Or maybe you want some math to back up your theory about whether there's a dependency. So we can use probabilities to check for independence. So there's kind of two ways that you can check, and this first one is my favorite one. If events A and events B are independent, then the conditional probability of A given B would be the same as the probability of A. In other words, A and B are independent if the occurrence of B doesn't affect the likelihood of A. Like it's the same probability either way. Whether or not B happened, the probability is the same. The other way you can check is if you multiply the probability of A and the probability of B together and it's equal to the probability of A and B occurring, then that's another way to tell that things are independent. Okay, so here is some information about a hockey team. So we have a hockey team who we've got the frequency of their wins and losses, and then we have the frequency of when the games went into overtime or not. So we're going to let event A represent the hockey team wins a game. So this is going to be A. That means this is not A, so I'm going to use that not squiggle. And B is representing the event that the games go into overtime, which makes this not B. Okay, find each of the probabilities. So the probability of A is 0.563. Overall, whether they're in overtime or not, they win 56% of the time. Probability of B, which is the probability of overtime, well, it looks like 23% of their games go into overtime, 0.231. So the probability of A and B, this means that they win and they were playing through overtime. So that would be this category, 0.107. And then our final one is a conditional probability. So we are going to have to do a little bit of math for this one. We want it to be out of, our given condition is B, that they went into overtime. So it's going to be out of 0.231. and the ones that they won are 0.107. So when we divide that, we get 0.463. So looking at our little list over here, does the probability of A given B equal the probability of A? And it looks like no, they do not. They're different by about 10%. Let's check the other one. The probability of A and B, that was 0.107. And now I want to multiply together the probability of A multiplied by the probability of B. So that's 0.563 multiplied by 0.231. And when we multiply those two together, we get 0.13. And again, you can see that those are not the same. They're closer than the previous one was, but they're definitely still not the same. So based on the results of these two questions, are the events winning the game and going into overtime dependent or independent? Well, if those probabilities are equal to each other, that's independent. So these are not equal, so these two events are independent. I'm sorry, oh my gosh. They're not equal, so they're dependent. And you can probably see why I prefer the first one. It's because I don't have to do an additional calculation. For the second check, you would have to do this additional calculation. So you can use this first check if you prefer it. All right, here we have a situation. We've got a suspected cause of disease. They think this genetic variation is causing the disease. So they collected some information about people, test them for the disease, and test them for the genetic variation. So if a person from this study is selected at random, we're going to let A represent that they have the disease. So this is not A, no disease. And then we'll have B represent that they have the genetic variation, which means this is not B. Okay, use a table to find each probability. Well, the probability of A is, let's see, we're going to actually have to math here. So 80 plus 1,050, our total here, 1,055. Whoa. Our total here is 1135, and we need our grand total as well. So we need to add up more things as well. So this is 1172. 2307, 92, and we'll just get all the totals really quick because I don't know which ones we'll need. 2215. And I like to add these two to make sure, especially when we're talking about quantities, these should definitely add up. And they do. Okay, perfect. So we've got all of our totals. So the probability of A is going to be 1135 divided by 2307. So it's the ones that have the disease out of the grand total, which gives us 0.49. I'll just do 2 decimal places here. Probability of B, so that's the probability of having the genetic variation. There's 92 people in the study that had the genetic variation out of 2307, so not a lot, not very likely at all. So that's only a 3%. Let's see. Let's say 4%. 0.04. Okay, so for the sake of the video, I am going to... Oh, the other one's cut off. For the sake of the video, I'm just going to check the conditional probability of A given B. So if these two things are independent, the probability I'm about to calculate should match the probability of A. So this is only out of the ones that have genetic variation. So we're focusing on this row of our table. We're given that they have the genetic variation. So it's out of 92 and it's 80 out of the 92. So that is 0.87, 87%. So our follow-up question is, based on these, are the events independent? Well, the probability of A was 0.49, 49%. And the probability of A given B, the probability of the disease given that we know they have the genetic variation, was 87%. These two things are not equal. So events A and B are dependent. So it looks like there might be a relationship between that genetic variation and the disease. And if you take a statistics course, you'll talk a lot more about whether, how to decide that. For the video, I'm skipping this question. Okay, example 6, last one. The table shows the results of an experiment where participants were given the choice of listening to music or not listening to music while sitting quietly in a room for a few minutes. Their heart rates were measured at the beginning and end of the experiment. We want to know, is there evidence to suggest that these events are independent? So let's do a comparison. Let's check their heart rate. So let's call this A. The probability of an increase in the heart rate. And then let's look at the probability that their heart rate increased given that they listened to music. So the probability of an increased heart rate is 40 out of 66. So it looks like our total is 66. So out of the 66 people, oh my gosh, my math today, 42, oh my goodness, 68. Just want you to know, I literally have my notes written out with all these numbers on them, and I still can't get it right. So, sorry. 42 out of 68. So the probability of A, 0.62. So the probability that their heart rate increases given that they're listening to music, so this time we're limiting ourselves just to the people listening to the music. So that would be 30 out of 48. And if I calculate that probability, 0.63. And so I think that we would say that these are independent, likely to be independent, because the probability of A is basically the same as the probability of A given music. Basically, their heart rate increased overall at the same rate that their heart rate increased if they were listening to music. So it doesn't seem like the music is having an effect. So what does it mean for two events to be independent? It means the occurrence of one doesn't affect the likelihood of the other. Wow, I cannot spell. So in this specific case, the occurrence of the music didn't affect the likelihood of an increased heart rate. Okay, so that is it for this lesson. You should have enough information to finish the rest of your assignment. Let me know, or your teacher know, if you have any questions. Thanks a lot.